At Washington National Airport, a Boeing 737 began its takeoff roll through falling snow. Both engine pressure ratio gauges reached a target setting of 2.04, yet the airplane needed almost 5,400 feet to leave the runway, nearly 2,000 feet farther than expected. Before liftoff, the first officer said the performance did not seem right. The engines kept running, but they were producing far less thrust than the gauges appeared to show. The captain continued. The aircraft climbed only a few hundred feet. Its stall warning began almost at once and continued as it crossed the boundary of the airport. 24 seconds after leaving the ground, Air Florida Flight 90 struck the northbound span of the 14th Street Bridge and entered the ice-covered Potomac River. 79 people had been aboard. 5 survived, 4 people on the bridge were killed. The airplane had been de-iced before departure. Its engines were still running. The EPR needles used to set takeoff power had reached the commanded number. Yet fresh contamination had formed on the wings, and the engines were producing much less thrust than that number suggested. The National Transportation Safety Board would connect those conditions to a third failure that remained available during the ground roll: the chance to stop. One problem changed the airflow around the wings. The other changed what the crew believed the engines were producing. Neither announced itself as a dramatic break. The airplane accelerated, the needles looked steady, and the runway passed beneath it. The contradiction was visible only in the time and distance the takeoff was consuming. How could a deiced 737 reach its target power indication and still leave the runway without enough thrust or lift to remain airborne? The answer begins before the engines accelerated, with a temporary protective layer, a long wait in continuing snow, and a cockpit instrument that did not measure thrust directly. By the time Flight 90 reached runway 36, the crew had seen fresh contamination, unusual engine indications, and acceleration that felt wrong. They did not identify the hidden measurement failure connecting those warnings. Flight 90 was scheduled to leave Washington for Florida at 2:15 that afternoon. It did not. Snow had been falling through the day, and Washington National closed for snow removal at 1:38. Runways, taxiways, ramps, aircraft, and ground equipment all entered the same cold weather system. Clearing one surface did not clear the others. Reopening the airport would only start a queue of airplanes that had been waiting in the storm. N-62AF had arrived from Miami at 1:29. 71 passengers and 3 infants boarded, joining 5 crew members. The aircraft sat at Gate 12 while the closure continued. Some passengers were traveling home. Others were connecting through Florida. Their individual reasons for being there would later appear in family accounts, but the operational fact was simpler. 79 people were waiting inside an airplane whose exterior condition kept changing. Contract workers began de-icing the left side at about 2:20. Roughly half an inch of wet snow had been observed before treatment. The work stopped after only a limited area because the airport would remain closed longer than expected. When de-icing resumed around 2:45, one operator completed the left side and another treated the right. The interruption mattered because this was not one continuous uniform pass over a stationary problem. The equipment introduced another uncertainty. The nozzle had been replaced, but the replacement did not deliver the intended concentration of glycol in the same way. A sample from the truck contained about 18% de-icing fluid when the selector called for 30%. Investigators found the procedures deficient but could not turn one mixture into the whole cause. Fresh snow appeared on treated surfaces within 10 to 15 minutes, and the airplane remained outdoors as the storm continued. De-icing removes contamination present at that moment. Anti-icing fluid can delay new accumulation, but its protection depends on concentration, weather, and elapsed time. In heavy wet snow, that useful window can close at the gate or in a taxi line. Investigators could not determine whether the aircraft was completely clean immediately after the treatment. They could determine that snow returned quickly and remained visible before takeoff. Treatment finished at about 3:10. Heavy snow was still falling. The jetway was retracted at 3:15, and a station manager saw a light dusting on part of the left wing. Then the first tug could not push the airplane backward on the slippery ramp. The crew tried to help by using reverse thrust. Snow and slush blew around the aircraft for an estimated 30 to 90 seconds, but the airplane did not move. Boeing guidance warned against using reverse thrust to push back in snow or slush. The NTSB said the attempt may have contributed to leading-edge contamination and blockage of the engine pressure probes. May is important. Investigators could not trace each piece of ice to that single maneuver. They could establish that the airplane spent more time in active precipitation and that the crew had placed it in a condition the winter procedures were meant to avoid. A second tug with chains arrived. Pushback began at 3:35, and Flight 90 was ready to taxi 3 minutes later. By takeoff, about 49 minutes had passed since de-icing ended. The exact condition of every part of the wing could not be reconstructed minute by minute. What could be reconstructed was the crew's own awareness. During taxi, they repeatedly talked about snow and ice on the aircraft. The first officer estimated that his wing carried roughly 1/4 to 1/2 inch of snow. The crew also discussed the warm exhaust from an aircraft ahead and whether it might clear the wings. Exhaust could warm one area while blowing moisture and contaminants toward another. It was not a controlled dicing method. The conversation shows that the crew knew the surface condition was changing and tried to reason about it without leaving the taxi queue. A return to the gate would have required another delay, another treatment, and a new place in a crowded departure sequence. Those costs were real, but they did not change the aerodynamic rule. The aircraft had to be free of adhering snow and ice before takeoff. Neither the captain nor the airline maintenance representative verified that condition before pushback and taxi. The NTSB also found that the aircraft was properly certificated and maintained, and that the crew held the required qualifications. The danger came from the way a serviceable airplane was prepared and operated in the storm, not from a hidden defect in its airworthiness certificate. The second failure began inside the engine's pressure sensing system. Flight 90's Boeing 737 used Pratt & Whitney JT8D engines. In the cockpit, the crew set takeoff thrust with engine pressure ratio, or EPR. EPR compares pressure at one part of the engine with pressure measured near the inlet. It is useful because thrust and pressure are related. It is not a scale that directly weighs the force pushing the airplane forward. One of the inputs came from the PT2 probe at the engine inlet. The probe sampled the pressure of the air entering the engine. Its reading became the lower part of a ratio. If that inlet value was wrong, the ratio could be wrong even while the gauge moved smoothly and looked precise. The instrument could only report the pressure information it received. The engine anti-ice system used hot compressor air to protect vulnerable inlet surfaces and pressure sensing. In icing conditions, it was meant to be selected before the measurement became unreliable, not after a crew had diagnosed a blockage. During the after-start checklist, the captain answered off to the engine anti-ice item. The switch remained off through taxi and takeoff. The NTSB later found that both PT2 probes became blocked by ice before the takeoff roll, leaving the cockpit with a precise-looking ratio built from a corrupted inlet value. A blocked PT2 probe could make indicated EPR rise faster than true engine pressure ratio. As the throttles advanced, the cockpit needles approached the 2.04 target. The crew could stop moving the throttles because the display said the engines had reached takeoff power. In reality, sound recorded on the cockpit voice recorder showed a much lower engine speed, equivalent to about 1.70 EPR. The NTSB calculated a shortfall of about 3,750 pounds of net thrust from each engine compared with a thrust associated with a true 2.04 EPR setting. The engines had not flamed out. They were producing steady thrust, just far less than takeoff required. That distinction matters because nothing dramatic in the sound or feel announced an engine failure. The danger appeared as slow acceleration and disagreement among instruments. EPR was not the only information available. Fan speed, core speed, exhaust gas temperature, and fuel flow would have shown values lower than expected for full takeoff power. A normal instrument scan should make those readings agree as a group. On Flight 90, EPR said the target had arrived while the supporting values and the aircraft's acceleration said it had not. The disagreement was harder to read than a warning light because each instrument still moved and each engine still responded. Cross-checking was the step that could turn those separate clues into one conclusion. The first officer noticed the disagreement during taxi. He called attention to a difference between the left and right engine indications. During the takeoff roll, he said the performance did not seem right and repeated that something was wrong. These were not insights created after the crash. They were observations made in the cockpit while the aircraft was still on the runway. Turning engine anti-ice on was not a magic way to add thrust. The system protected the pressure measurement and made correct power setting possible. The full defense was procedural. Use anti-ice in icing conditions, set power, and cross-check the rest of the engine instruments. A crew familiar with winter operations would expect the anti-ice system to alter engine indications and would account for that when setting thrust. Flight 90's crew had limited jet transport winter experience. They reached the runway with the protective system off, and with one apparently reassuring gauge carrying more authority than the aircraft's slower physical response. Low thrust explains the slow acceleration. The immediate stick shaker after liftoff points to the second mechanism. A wing produces lift by creating a pressure difference as air follows its shape. The useful shape includes the condition of the surface the air actually meets. A thin, rough layer of frozen contamination can change that shape at the most sensitive place, then make a normal rotation produce an abnormal response. On a clean wing, airflow can remain attached as the angle of attack increases. Roughness near the leading edge can make it separate sooner, reducing maximum lift and increasing drag. The wing may then approach a stall at a speed that would be safe for the clean airplane. Flight 90's speed calculations described a clean aircraft. The surface moving through the snow was no longer the surface used to produce those numbers. The 737 to 200 also had a known pitch-up tendency when the leading edge was contaminated. At rotation, the nose could rise more sharply than expected. That increased angle of attack further disturbed the airflow, which reduced lift and increased drag at the moment the aircraft needed both lift and acceleration. The control input did not need to be extreme for the contaminated aircraft to answer differently. The stick shaker was designed to warn that the wing was approaching a stall. It responded to angle of attack, not to whether the surface had been inspected. On Flight 90, it activated almost immediately after liftoff. Its signal was consistent with the reduced aerodynamic margin investigators reconstructed from the contaminated wing and the aircraft's unusually high pitch attitude. The engines and wings now made each other's problem worse. Reduced thrust lengthened the ground roll and left less speed in reserve. Wing contamination demanded more speed and more thrust while producing extra drag. After rotation, the pitched-up aircraft needed acceleration it could not create. Its airspeed decayed even though the engines continued running. Investigators tested the mechanisms separately. A clean aircraft with the observed thrust should still have climbed at more than 1,000 feet per minute. With normal takeoff thrust, the contaminated aircraft should not have lost flight in the way recorded. These were analytical comparisons, not claims that either condition was safe. They showed why the accident required the combined loss of thrust and lift margin. The snow did not have to form a visible block, and the engines did not have to fall silent. The failures appeared as roughness, low secondary indications, and a takeoff roll that kept consuming runway. Together, they created an airplane that could reach rotation speed by indication, leave the ground, and still lack the performance needed to climb. Flight 90 joined a line for runway 36 behind other departing aircraft. Taxi time gave the crew more chances to observe the snow, but it also normalized the condition. Other jets were moving. The runway had reopened. A sequence of routine clearances carried the airplane closer to departure. Nothing in that flow could verify the wing surface or the engine pressure probes for the pilots. At 3:58, the crew completed the pre-takeoff checklist. The target EPR was 2.04, decision speed was 138 knots, rotation speed 140, and the planned climb speed 144. Those performance calculations assumed a clean airplane with its systems providing valid information. Adhering snow was a reason not to take off, not a condition that could be corrected by entering a different number. The tower cleared Flight 90 into position and hold at 3 hours 58 minutes and 55 seconds. 29 seconds later came the takeoff clearance. 4 seconds after that, the controller told the crew not to delay because landing traffic was 2.5 miles away. The NTSB found that the spacing violated separation requirements. It did not identify the controller's action as a probable cause of the crash. And the instruction added pressure in the cockpit, but it did not establish that the airplane was safe to fly. A crew may refuse a clearance or reject a takeoff when performance is wrong. The controller compressed the moment while control of the throttles and brakes remained in the cockpit. Engine spool-up began at 3 hours 59 minutes and 45 seconds. The captain transferred the throttles to the first officer, who advanced them while the captain monitored the instruments. The EPR needles reached their target, but the other indications remained low. 13 seconds after spool-up began, the first officer said the performance did not seem right. He was not describing a small difference discovered later on a graph. He was feeling the runway pass beneath an aircraft that was taking too long to accelerate. As the roll continued, he repeated that something was wrong. The captain answered that the condition was all right and kept the takeoff moving. The NTSB reconstructed acceleration from recorded sound, elapsed time, distance, witness evidence, and aircraft performance. At the first officer's initial concern, the airplane had been rolling for only a short time and remained well below decision speed. A reject did not require the crew to name the failed probe. The slow acceleration and mismatched instruments already supplied the reason to stop. A rejected takeoff would have carried its own risks on a winter runway. The board's analysis still found enough distance to stop safely when the abnormal performance was first recognized. Each second that followed added speed and removed pavement. Continuing exchanged a controllable ground problem for a flight problem whose mechanism the crew had not identified. Once rotation began, the only remaining test was whether the real thrust and the real wing could support flight. The takeoff roll lasted about 45 seconds. A normal roll under the expected conditions would have taken roughly 30. The aircraft used nearly 5,400 feet instead of about 3,500. At the speed Flight 90 was gathering, 15 extra seconds represented thousands of feet of pavement, more engine noise without the expected acceleration, and a liftoff point moving steadily closer to the end of the airport. The difference unfolded through the windshield one centerline stripe at a time. And at rotation, the contaminated aircraft pitched up. The nose rose, the main wheels left the runway, and the stall warning began. The airplane had passed every remaining ground defense. From this point, the crew could only work with the thrust, lift, altitude, and distance they had carried into the air. Flight 90 initially climbed, but it did not accelerate. Its angle of attack stayed high and its speed began to decay. The first officer called for the nose to come down. The captain tried to control the pitch while the stick shaker continued through the control column. Lowering the nose could reduce the stall condition, but there was almost no altitude to trade for speed. Holding the nose up protected height for a moment while adding drag. Investigators later used performance simulation to place the likely peak altitude at only a few hundred feet, not a precise recorded maximum. The aircraft remained in that narrowing exchange as it crossed the airport boundary toward buildings, highways, and the river. Ahead lay the 14th Street Bridge complex, carrying afternoon traffic across the Potomac during the evening commute. The departure end of runway 36 was about 3/4 of a nautical mile from the northbound span. A normal 737 would cross that distance while climbing away from the river. Flight 90 reached it only 24 seconds after liftoff. Still slow, still near stall, and only high enough for its landing gear and fuselage to meet the traffic below. Geography turned a failed climb into a second disaster on the ground. The aircraft struck vehicles and the bridge structure then entered the river. 4 people on the bridge were killed. There was no post-impact fire. The force broke most of the fuselage apart in the frozen water and spread debris through an active rescue scene beneath the span. Part of the rear cabin remained comparatively intact. Its structure protected a small pocket through the first impact, but the people inside still had to escape into freezing water with the shoreline beyond the ice. Survival depended first on where the cabin broke, then on whether rescue could arrive before cold and exhaustion took away their remaining strength. 6 occupants emerged from the wreckage through the comparatively intact aft cabin area. That survival pattern mattered to investigators because it showed that the impact was not uniformly unsurvivable. A small protected space remained, then placed its occupants into a different lethal environment. The water was about 34 degrees Fahrenheit. Ice, current, debris, heavy clothing, and injuries turned every minute into a loss of strength. Life vests were difficult to retrieve and use after the cabin broke apart. The survivors remained in the water for roughly 22 to 35 minutes. One of the 6 who escaped later drowned. The final count was 5 survivors from the airplane, 4 passengers and 1 flight attendant. Airport rescue units did not immediately know where the aircraft had gone. Personnel became aware of the accident at 4:03 and received official notification at 4:04 after the tower tried to establish the flight's location. The airport met the rescue requirements then in force, but those requirements did not demand equipment for an ice-covered river. Its airboat had not been tested on ice and proved ineffective. A runway emergency had become a water rescue outside the system's practical reach. A United States Park Police helicopter reached the river with pilot Donald Usher and paramedic Melvin Windsor. They adapted a rescue line while hovering low between bridge structure, ice, debris, gusting rotor wash, and people losing strength in the water. The cable had to reach one survivor at a time, then carry that person toward a crowded bank. Between about 4:22 and 4:35, the crew brought 4 passengers and 1 crew member to shore. Passenger Arland Williams repeatedly passed the line to other survivors before the helicopter returned for him. He was no longer at the wreckage when it came back. When Priscilla Tirado could not hold the line, Congressional Budget Office employee Lenny Skutnik entered the water from the bank and helped her reach shore. Their actions became the public memory of the rescue. The report recorded a narrower institutional fact. Water rescue equipment was not required, and the available capability could not handle the ice. The NTSB did not assign the crash to one failed machine or one winter mistake. Its probable cause named 3 crew actions. Engine anti-ice was not used, the aircraft took off with contamination on its airfoils, and the captain did not reject after abnormal engine readings were called out. Each decision removed a defense against the physical conditions already present. The contributing factors were the prolonged delay and continuing precipitation, the 737's pitch-up behavior with leading-edge contamination, and the crew's limited experience in jet transport winter operations. Other findings addressed deficient de-icing procedures, fluid concentration, verification, instrument cross-checking, and the limits of winter water rescue. The same physical conditions appeared across ramp work, cockpit procedure, training, and emergency response. The response followed the mechanisms investigators had found. Manuals clarified that engine anti-ice had to be used during ground and flight operations when icing existed or was expected. Crews were directed to compare EPR with other engine indications when pro-blockage was possible. Early recommendations called for a visual wing inspection after more than 20 minutes in continuing snow or freezing precipitation. Other work addressed de-icing practice, gate holds, winter training, runway information, and emergency response. Some actions were recommendations, others became documented manual or equipment changes. Flight 90 accelerated a broader winter operations effort rather than creating every safeguard on its own. A Washington National rescue preparation also changed. By the time the report was published, the FAA had acquired ice-capable boats, trained police and firefighters for ice operations, obtained rescue nets, and begun diver training. The response separated 2 problems that the accident had forced together. Aviation rescue had to reach beyond the airport fence, and local agencies had to be able to work in water that was partly frozen. Those measures addressed the emergency after impact. The earlier defenses still depended on keeping contamination off the aircraft, preserving valid engine information, and stopping a takeoff that did not perform as expected. The answer lay in the pressure information feeding one cockpit gauge. The blocked PT-2 probes let EPR reach 2.04 before the engines reached the required thrust. Other instruments and the long ground roll disagreed. At the same time, fresh contamination reduced the wing's lift margin and changed its pitch response at rotation. The aircraft left the runway with both shortages at once. Well, the accident began long before the bridge, but it remained preventable after several defenses had already failed. The clearest warning was not hidden in wreckage. It was spoken during the takeoff roll. The performance did not seem right. A safe system has to make that observation actionable before momentum, procedure, and a reassuring gauge carry the airplane beyond the last place it can stop.